So this is still Unit 1, Part D. And just as a reminder, we are in the process of using these special limits in combination with the limit laws to find our limits. When I look at this next example, at first glance, this doesn't really look a whole lot like any of our three special limits that we've been dealing with. And so instead on this one, I'm going to say maybe it's time to start considering some trig identities. This one isn't a particularly complicated trig identity, so you probably don't need a list, but I do want to point out to you that one of the things that you have available to you is this list of trig identities. It's in your course pack along with all of the other notes that you're allowed to use. Even when we do proctored exams, you will be able to use these. So in this case, as I'm looking at this particular identity, I'm going to say, or this particular problem rather, I'm going to say that if I want the limit of 1 minus cotangent 4x times sine 4x over x, my biggest concern right now is the fact that cotangent wasn't a part of any of the three special limits. So I'd kind of like to get rid of that. I'll use an identity to say that cotangent is just cosine over sine. So let's do that rewrite first of all. Okay. If nothing else, that makes it easier for me to see what's going on. And I can right away see that there's going to be some algebra that I can do here. The sine 4x's I can divide out. So I end up with the limit as x goes to 0 of 1 minus cosine 4x over x. All right, that puts me in a much better place. Now I'm starting to recognize that as probably being a lot like this one. I'm not quite there yet because the argument has to match the denominator, and I don't have that yet. So let's go ahead and kind of run through the work. Now that I've got that simplification made, it's a little easier for me to first of all just check that we have the indeterminate form. So let's do that real quick. This would be 1 minus cosine 0 over 0. And cosine of 0 is 1. So I do indeed have, 1 minus 1 is 0 over 0. Our indeterminate form that we've seen over and over here. And so I'm thinking, yep, probably that special limit is what I need. Now I have to have the argument and the denominator match. Otherwise, I don't have an exact match for this form. So I cannot change the argument of the trig function easily. It's much easier to change the x in the bottom, the one that's not in the argument. If I want that to be a 4x, all I really have to do is multiply it by 4. And again, of course, I'll be careful to multiply by 4 over 4, so I don't change the value of my expression. All right. I really want this 4 to go along with that x so that the denominator and the argument match. So I want to keep those together. And this extra factor of 4 up here, constant multipliers can just get pulled out of limits, remember. So I'm going to take that 4 and bring it out in front. It's one of my limit laws. What I have left now is exactly what I need. The argument and the denominator match perfectly. We'll just make a quick little u equals 4x. And since x is approaching 0, that means u will also approach 0. And sorry, I'm running out of space here. Let's see if I can squeeze this in over here. I've still got that 4 out in front. And I'll now make this the limit as u approaches 0 of 1 minus the cosine of u over u. Other than the change in variables, that's now a perfect match for the special limit, and so its value is 0. So I have 4 times 0, or 0. And once again, for the third time in a row, notice, we have a hole at 0, 0. Once again, for the third time in a row, we have a very different technique that we had to use to justify that limit. So make sure you're justifying your limits appropriately. All right. On this next one, we're looking for the limit as x approaches 0 of the tangent of 8x over 5x. And let's start again by checking to make sure what kind of form we have. If we are to substitute in, we would have the tangent of 0 over 0. Tangent of 0 is 0, so we have the indeterminate form, 0 over 0. All right, got to do some work here. And right now, it doesn't look like any of my 3 special forms, but again, I'm going to notice that tangent's not part of any of them. So it might be a good idea to use a trig identity first to get rid of the tangent, and then I'll maybe be able to recognize something. So let's do that. I'm going to rewrite the tangent of 8x as sine 8x over cosine 8x. And now here's one of my very favorite algebra tricks. You'll see me use this a lot this semester, so it's cropping up for the first time. Here we go. I don't like complex fractions. I could put this whole thing over 5x, but because that's messy, what I'm going to do instead is write it as times the reciprocal, right? Dividing by 5x is the same as multiplying by 1 over 5x. So again, super common algebra trick that you'll see me use a lot. Change division into multiplication by the reciprocal. All right, well, let's see. Let's start thinking about what we've got and where the problem really lies. This cosine 8x doesn't really bother me much because as x goes to 0, the cosine of 0 is 1, and I don't mind having a 1 in the denominator. So that's not really a big problem for me. The 5 is also not a problem. It's just a constant multiplier, really 1/5, and I could pull that out as a multiplier in front of the limit. So with that in mind, I'm going to do a rewrite. I'm going to say I have the limit as x goes to 0. That 5, I'm going to actually pull that out, squeeze that out in front here. And then I'm going to write this as the sine of 8x over that x. That's still a problem, but notice it's a lot closer now to one of the special limits that we have. And then I'm going to separate this off as a separate one, the limit as x goes to 0 of 1 over the cosine of 8x. We already said that's not going to be a problem since the denominator is not 0, so I'm just kind of getting it out of my way. Okay. Take a look through here and just convince yourself that we haven't lost anything. It's all still there. The sine 8x is here. The cosine 8x is here. The 5 is out in front. The x is still in the denominator here. And again, the 5 is still in the denominator, right? We haven't moved anything around. We haven't lost anything. It's all still there. All right, we're almost to what we need now. The 1/5 and this last limit aren't going to be any problem at all. This one, though, I need the argument to match the denominator. We've seen this a few times. Hard to change the argument, but not so difficult to change the denominator. Let's multiply by 8 over 8. I would really like to keep all of that together, to keep the 8x in the denominator to match the argument of the sine function. This 8 is in my way. It's a constant multiplier. I'm going to pull that out in front. So I'm now going to make this 8 over 5. Let's also do a u substitution. Let's let u be 8x. And since x is approaching 0, u will also approach 0. So this limit could be written as the limit as u approaches 0, and that will be sine u over u. And then this last limit, I'm not going to change that at all. We already know that one's not going to be a problem. All right, again, take a quick look. Convince yourself it's all still there. And then we can finish our limit. This limit is now a perfect match for our special limit. Its value is 1. This limit has 1 in the numerator, and then we have cosine of 0 in the denominator, which is no problem since that's just 1. So we really have 8/5 times 1 times 1, or 8/5. So we've got a finite limit. Originally it was an indeterminate form, so we know there's no y value. This graph would have a hole at 0, 8/5. All right, if this seems like a lot of work and you feel like, hey, wait a minute, I could have gone back, I see the 8, I see the 5. It's true, but again, the whole purpose of doing this is to show that these limits exist analytically. And so it's really, really important that you go through the mathematical strategy so your reader, in this case me, who's also your grader, right, can actually see that you understand those limit properties and why the limit turns out the way it does. All right, I'd like to end this section with one special case. When we have piecewise functions, we have to be a little bit more cautious because we have multiple different expressions that we substitute into at different times. Therefore, when you are finding limits with piecewise functions, anytime the limit exists at what I call the breakpoints in the domain, you must also consider, whoops, and I wrote that badly, you must also consider the two one-sided limits. Because usually when that happens, when you're at one of the breakpoints in the domain, like here -3 and 0 is where the function is broken up, you're going to have a different function approaching from the left than from the right. So it's going to be important to do the one-sided limits. Keep in mind the overall limit only exists if both one-sided limits are equal. So let's start with the limit as x approaches -3. That is one of those breakpoints in the domain, which means I'm going to immediately say I'll have to do two one-sided limits. Let's start with the limit as x approaches 0 from the left. If we're approaching -3 from the left. If we're approaching -3 from the left, that would be numbers smaller than -3. We'd be using the function x squared minus 5. And remember, you always try plugging in first, direct substitution, and that's not going to be a problem, right? If you plug in -3, you're just going to get 9 minus 5, or 4. No problem. Now let's also find the limit as x approaches -3 from the right. If we're approaching from the right, we'd have x's that are bigger than -3, so we'd be using the x plus 2 as our expression. And once again, we're just going to plug into that. -3 plus 2 is -1. So the limits from the left and the right are different. meaning the original double-sided limit doesn't exist. And by the way, it's really important to state that. That shows me that you've noticed what's going on. You haven't just done the one-sided limits. You've actually completed it and shown that and that you understand that the double-sided limit doesn't exist. These are both finite numbers, so it's not an asymptote, right? This is one of those jumps in the graph. Approaching from the left, we approach one point. Approaching from the right, we approach the other. So this is actually a jump in the graph. All right, let's try that same idea, approaching 0. Once again, notice that 0 is again a breakpoint in the domain. We change our expression at x equals 0. So that means I will once again have to consider the two one-sided limits. First of all, the limit as x approaches 0 from the left. 0 from the left means my numbers are less than 0. So I'd be here. And I'm looking at x plus 2. Direct substitution gives me 0 plus 2, or 2. Now what about the limit as we approach 0 from the right? That would mean numbers bigger than 0. So we're here. And we're going to use the expression 2 cosine x. Again, we always try direct substitution first. So plug that 0 in for x. And since the cosine of 0 is 1, that's 2 times 1, or 2. This time, we got the same limit from the left and the right. So the limit is actually 2. We have a finite limit. This is a point of continuity on the graph. All right, one more. What if we want to take the limit as x approaches -2? Notice that -2, cut it off for you. Notice that -2 is not one of the points where the domain gets broken up. -2 is actually entirely within this middle section. And therefore, I don't have to consider the one-sided limits. Instead, I can just say this is the limit as x approaches -2, and we'd be using this expression, x plus 2. Plug in your value, and your limit is simply 0, and you're done. The graph would show that we are continuous at the point -2, 0. All right, one last little hint about piecewise functions. I probably should have said this right away, and I kind of forgot, to be honest with you. But sometimes my students tell me they have a hard time kind of figuring out which expressions to use in which parts of the limit. And there's a little diagram, if that's true for you. There's a little diagram that you can use to help yourself out. What I recommend, if that's a challenge for you, is try this. Before you ever do the limits, make yourself a little number line. This graph gets broken up at -3 and again at 0. When we're less than or equal to -3, we use the function x squared minus 5. Between -3 and 0, we use the function x plus 2. And when x is bigger than 0, we use the function 2 cosine x. That can sometimes be a really big help when you're doing these left and right limits. Because now when I come down here and say I want to approach -3 from the left, it's really easy to just look to the left of -3 and figure out which expression you need to use. So if it helps you to create that little number line first, I would encourage you to do that. All right, I know this was a long section. We are finally at the end of Unit 1, Section D.